Okay, in this video I want to talk a little bit about recording. So that is when we want to take a sound and usually convert that into an electrical signal like we talked about in the last video. But maybe we don't want to play that back right away. Maybe we want to store it somehow in order to play it back again later. And so I'm going to talk about two types of recording. One of the earliest type of recording, which is a type of recording called an analog recording, and the specific mechanism is the one that we use on a LP record or a vinyl record. And then I'm going to talk about the modern way that we mostly record music, which is digitally. Okay, so basically the idea of making a recording is to take that electrical signal that is encoding your sound wave and encode that in some physical object. And so the simplest thing you can imagine is actually just taking the electrical signal and then somehow making the time graph for the current for that electrical signal, which is the time graph for the sound wave, somehow just writing that down or drawing it somehow. And that's pretty much exactly the way that a vinyl record stores sounds. So a vinyl record has grooves that go round and round and round in a spiral pattern on the disc. But if you look very closely at the grooves under a microscope, you see that the edges of the grooves are actually ripply. And what that is actually precisely is a pattern that precisely reproduces the time graph for a sound wave that we're recording. Okay, so I want to talk about how you would do that and then how you would actually play back the sound. And fortunately, it uses exactly the same physics that we already just talked about in the last video for making a speaker and making a microphone. Okay, so when you're making an LP record, you use something that's very much like a speaker. So you have a coil of wire, you have a permanent magnet, and then you're going to send your electrical signal to the coil, and then the magnet will move back and forth in response to that. But this time, instead of being connected to a membrane or a plate, your magnet is connected to some object that can etch the surface of our disc. Okay, so this would be called our master disc, the one we're originally making the recording onto. And so this cutter, it makes a groove in the disc. So what you do is you take the disc and you just have it rotate around at a certain rate, usually 33 1/3 times per minute. And so if you didn't supply any current to this coil, and the cutter would just make a smooth groove in a spiral pattern. But because we're sending in this current and the magnet's moving back and forth a little bit, then the cutter also moves back and forth a little bit as the disc rotates around. And so that's how you end up with this specific shape for the edges of your groove that reproduces the time graph for the sound wave that we're trying to record. Okay, so it reproduces whatever electrical signal you send in, that determines the shape of the groove, of the edge of the groove. Okay, so that way you've got a physical recording, an etching almost onto the surface of the disc, and then you can use various ways of reproducing that disc into various copies. And so then your copy is this piece of vinyl with a groove that's very similar or hopefully identical to the one that you originally cut. Okay, so next, if you want to play that back, then it's just the principle that we used for the microphone. At least that's one type of record player. Something with a record player that has what's called a magnetic cartridge works in this way. So how does it work? Well, now you have a player that has this object that we call the cartridge, and coming out of that is a little needle that fits into the groove in your vinyl record. And so again, the record is spun around at the same rate as before. And if there was actually some sound that you recorded, now the needle is going to move back and forth because the groove isn't exactly smooth. So it has these ripples in it. And so now the needle moves back and forth, and the time graph for that motion would be determined by the shape of the groove. Okay, so that's going to be now similar to the time graph for the sound that we want to produce. Okay, but what we do first before actually playing that through a speaker is convert the motion of this needle into an electrical signal. And that's done in the same way that we had for the microphone. So the needle, one way to do this is have the needle attached to a magnet, which then moves back and forth relative to a coil. And then this electromagnetic induction process that we talked about last time causes there to be a current in the wire whose time graph replicates the pattern on the record. Okay, so you have the ripply groove on the disc, the motion of the needle in time then mimics that. That causes an electrical signal through this process of electromagnetic induction, and then you could send that electrical signal to an amplifier and then to a speaker. Okay, so that is one of the earliest, maybe the earliest way that people recorded and played back music. It's still being used today. Some people think that the sound of vinyl records has a special quality to it that can't be reproduced through digital music. Other people think that's nonsense. But what I want to do for the rest of this video is talk about this more modern way of recording music, okay, which is what we call digital instead of analog. So let me just emphasize the distinction between these two things. Okay, so an analog recording is a recording that captures essentially all of the information about the time graph. And so you saw with the LP record, then the time graph for the sound wave was kind of reproduced with all its smooth features as the shape of the groove on the record. Okay, so in some sense, your analog recording is a complete graph transcribed somehow onto the record or onto some other medium like a magnetic tape. A digital recording, on the other hand, it's actually only capturing a part of that information. And so basically what you do for a digital recording is you take your electrical signal, and that goes into what's called an analog to digital converter. And that essentially just looks at the signal at a bunch of specific times. Okay, so at a certain frequency, it looks at the signal that's coming in, and then it just records, is that positive, is it negative, and what is the value? Okay. And so if you've used Audacity and you've ever zoomed in a lot onto the time graph, onto the waveform, then you'll actually see that at some point it's no longer smooth. It's actually just a bunch of dots. It looks like this. And so that gives you an idea of what the information in a digital recording would be. Okay, so basically just at these certain specific times, we would do what's called sampling the electrical signal, and then we just record the value of it. Okay, and then wait till the next time, record the value, wait till the next time, record the value. Okay, so there's only a discrete set of times that are being used. And then also the values for the amplitudes, whereas in an analog recording, they could really be anything. They could vary continuously. In a digital recording, there's only a certain number of specific values. So in terms of like the volume of the sound, we wouldn't be sensitive to any change. There'd be a certain limit. And so we just have a certain discrete set of possible volumes that we're going to assign to the sound or to the electrical signal at that instant. Okay. So your analog to digital converter takes in this smooth analog electrical signal that might be coming from our microphone, and it just converts that into a list of numbers that are stored in the computer memory. These numbers being the values of our graph at the various times. So the strength of the signal and whether it's positive or negative at all these various times. Okay, so there's a couple of important parameters that are useful to understand when we're talking about digital recording. And the first one is called the sample rate. It's just how often are you going to look at or sample the electrical signal, the analog electrical signal. Okay, so this is typically a very high frequency, higher than the kinds of frequencies that we can hear, and there's a good reason for that I'll explain shortly. And so a very common value would be 44,100 hertz. And so that means that 44,100 times per second, the analog to digital converter is looking at that electrical signal and seeing what the value of the current would be. The other important parameter is what's called the bit depth, and that is how many different values are you going to assign to say what the strength of the signal is. And so a typical value for that in what we call 16-bit recordings would be this number 2 to the power 16, or 65,536. You also see 24-bit recordings, and so that would be a much bigger number, 2 to the 24, and then you'd have over 1 million different possible values. Okay, so this kind of just determines how sensitive you are to small changes in the strength of the signal or the volume. Okay, so just to help you understand this a little bit better, I've got another example here, where on the top is a graph representing an analog signal, and on the bottom is the digital version of that. Okay, so this could be the time graph for a sound wave, and this would be our digital representation. And so you see that it's discrete both in time. We only look at the value at certain specific times, and then at each of those times we record a value which is perhaps not the precise value of the signal, but rather some discretized version. So we only have certain values that we're allowed to assign. And so even though this one is changing smoothly and decreasing and increasing, the digital signal might represent that as a flat portion before it goes up again. Okay. And you see you're going to get better resolution the higher your sample rate is. So the more often you sample it, and the more possible values for the strength of the signal that you use, so the higher the sample rate, the higher the bit depth, the more faithfully your digital signal is, your digital encoding is going to record the information that was present in that analog signal. Okay, so in terms of choosing the sample rate, well, how high should you have it? The reason that we don't just have it as high as possible is that it just is maybe too much information. We have to store all of that information, and if the sample rate or the bit depth are too high, you just get these enormous computer files. Okay, so what you want is to make it as low as possible so you're not sacrificing quality. And just a rough guide is that you want to have the sample rate at least twice as much as the frequencies of sounds that you're hoping to record. Okay, and so the reason is that if the frequency of sound is too high compared to the sample rate, then you're not going to faithfully represent it in the digital recording. And so this example that I have here really emphasizes that. So what it is just a pure sine wave whose frequency is half of the sample rate. But what you see is that every time we take a sample of that, the value of the graph is back down to 0. So it's 0, and then we wait, and the actual wave goes up and then down, or the signal goes up and then down. But by the time we sample it again, it's back to 0, and then 0, and then 0, and then 0. So you could have that sine wave, that would be like a pure tone sound at a frequency that's half the sample rate, and we wouldn't record that at all. So the digital version of that wouldn't see any of the features. Okay. And so basically that shows you that if your frequency is half the sample rate or higher than that, then you're going to have problems. You're not really storing that information. Okay, so what we want in making a recording is to record all of the sounds that we can actually hear, which could be, in the best case, up to about 20,000 hertz. And so we take the sample rate to be at least double that. And so that's why you commonly see sample rates of 44,100 hertz. That's one of the standards, or 48,000 hertz is another standard. And sometimes you'll see sample rates that are higher than that. So sometimes digital music is stored at a higher sample rate, and that would be because, well, maybe just going double the highest frequency you want to record is not quite enough to get all of the features. So some people can hear the difference between sampling at 44,000 hertz and some higher sample rates. Okay. So just finally, I want to mention the particular kinds of computer files that this information would be stored in. So you hear about WAV files and MP3 files and other kinds of files. And so those are basically the digital recordings. Okay, so an MP3 file or a WAV file is just a computer file that has all of the information about one of these digital recordings. A WAV file is basically just this list of numbers. It's just the list of numbers keeping track of the shape of a sound wave that you're trying to record. An MP3 file is kind of a condensed version of that. There's a way to take that list of numbers and store it in a way that's more efficient, and then you could convert it back into the regular digital signal before playing it. Okay, so that's basically how it works. If you want to play one of these digital signals, then you just use the opposite of the of the analog to digital converter. So there's some digital to analog converter that takes in all these numbers and then converts it into an analog electrical signal that you then send to your speaker.